All right, this is going to be the video notes for Rational Numbers Part 1. This is the first set of notes in our new packets for Unit 4. So if you don't have one, make sure to either print one off or go get one from your teacher. On your planner, you can write rational numbers. Be sure that you get the project, the brochure project, get that turned in by Friday. All right, so in your new packet, make sure to write down your name. My name is Mr. Thawson. My teacher's name is Mr. Thorson. And I'm in period, what is this? This is a YouTube video, so I'm in period YouTube apparently. So, yes, if you don't have me and you have Miss Kiro, you're probably confused why I wrote down my name is Mr. Thawson, but that's okay. All right. So, a rational number is any number in the whole wide world that we can represent in the form of P over Q, where Q does not equal 0. Essentially, that means if you can write it as a fraction, it is a rational number. Fractions can never have denominators of 0 until you hit calculus 2, which is a long time away for you. And that still is dependent on context. So it breaks math unless if you know other stuff. So it's not allowed. There's a conversation that we'll have later this year. But just know that you can never have a denominator of 0. So rational numbers are down here. These all can be written as fractions. And there are different classifications within the rational numbers. Natural numbers are the numbers that we generally think about when you're told to start counting. You don't normally say 0, 1. You normally go right to 1 and continue going up by the whole numbers. Next, we have the whole numbers. Those are the same, but they also include 0. So 0 is included. Then we have the integers. Integers are pretty much whole numbers and their negative counterparts. So they have negatives in them, they have zeros, they don't have any decimals or any weirdness going on yet. And then rational numbers are all of those things in between. So it's all of the fractions, all of the decimals, as long as they either terminate or repeat, which we are going to get to later. If you can write them as a fraction, they go in the rational numbers. There are some numbers that fall outside of that, called irrational numbers. These are numbers that never end. They will never, ever end. And they don't have any pattern, no repeating, no nothing. So pi is one of those examples. Square roots that are not clean square roots. So this is a 7th grade standard, so you don't know this yet. But the square root of 4 is essentially asking what times itself equals 4. And that's going to be 2. Because 2 times 2 equals 4. Right, so the square root of 4 is going to be 2. What times itself equals 2, you might be wondering? And it is an absolutely disgusting number that goes on forever and ever and ever and has no pattern, no cleanliness, and it's very irrational. So those ones that are not perfect squares are going to end up being irrational. There are some other constants that exist that are similar to pi, such as Euler's number. Those also do exist in the irrational numbers category. All right. All numbers except for 1 can be classified in one of these categories. All right. On page 111, that's the same page we're on. So there are 4 main categories. The first one is going to be the natural numbers. These are the numbers that we typically count by 1, 2, 3, 4, 5, and it keeps going. You will notice that we gave you the shortcut, which looks like that. If you ever decide to get a degree in mathematics, a lot of times you take a lot of shorthands, so you don't have to write out a bunch of words. This is what that is, pretty much. All right. On page 112, we have something that's represented by a W. And it's the natural numbers plus 0. Take a guess on what you think it is. It's the whole numbers. Next, we have the whole numbers, but they can be positive, negative, or 0. is represented by a z for some reason, and that is the integers. One reason that they couldn't have used I, if you're sitting there wondering why they didn't use I, is because if you know Roman numerals, that's actually 2. So that kind of rules out using I. Lowercase I also would be ruled out because that's an imaginary number, which you'll get to much, much later in life. All right, and then for the next one, we have everything in between. We have all the decimals, as long as they terminate or repeat. If you can represent it as a fraction, where q does not equal 0, then it is considered a rational number. That one's represented by q. You might be sitting there thinking, that's pretty random, but it's not. Q, in math, you probably think of a word called quotient. Or you probably think of the word quotient. And that is the answer to a division problem. Remember, fractions are division problems. So whatever you get, that's supposed to be an answer, not a circle. Not a 0, sorry. So whatever you get to that division problem or fraction would be a quotient, which is a rational number. So that's one reason that they chose Q. All right, so those are a bunch of qualifications or a bunch of categorizations of these numbers that we call rational. And on the CYU that's coming later this week, you will have to do that with a few numbers. All right, now we have to match the definition to the word. So we have terminating decimals and repeating decimals. You've been working with both of these already this year, and you'll work with them more. Try to figure out which definition makes the most sense to go with which word. Terminating decimal is a decimal that ends. If you were to get terminated from a job, do you still go there the next day? Hopefully you said no because you got fired. Your time there has ended, right? So terminating is a word that we use to describe ending. Repeating is pretty straightforward. It just means it repeats. It happens over and over and over again, right? The sun is repeatedly rising every morning. A decimal that has a pattern that repeats. Example 0.2 with a vinculum over it. We're about to learn that word here soon. It's the same as the 2's go on forever and ever and ever. All right, all of those can be written as a fraction. Fun fact, I'll show you what they are. You don't need to write this down. You don't need to know this yet. But you can write all of these as fractions relatively simply once you know the trick. So they are considered rational numbers. When a decimal ends, they are also considered rational numbers because you can write them as a fraction quite easily as well. So all of those would be considered rational numbers. All right. There is a little journaling prompt. Sorry, I jumped ahead there. There is a classification thing I want you to do. I want you to determine, are these rational numbers, yes or no? Look at all 3 of these numbers. Write down, yes, they are rational, or no, they are irrational. Pause the video and try that out. All right. This first one. Yes, it is rational. The decimal terminates, meaning you can write it as a fraction. This one, it repeats, meaning you can write it as a fraction, so it is rational. And then this last one, there is no decimal. It's just a whole and natural number, and it can be written as a fraction just by throwing it over 1. So all 3 of them are actually rational. Now I want you to think about that little dash thingy that we see right here. What does it mean? Take some time, write out your answer, and then play the video once you get that written down. All right, I would say that it means that the number Could be more. So the number or numbers repeats forever and ever and ever and ever. And I'm going to put a little line over it because that and ever would repeat forever and ever. All right, that's my sort of silly reasoning, or sort of silly answer. All right, flip the page to 113. We got our first comic of the packet. Einstein asks, what is that dash thingy called? That thing? And Johannes Kepler says, bruh, it's a vinculum. Didn't expect that to come from Johannes Kepler, but it did. So we call that thing a vinculum. You hear me say that quite a bit. It's really not that essential to know that that's what it's called, but it's kind of nice to have that clear communication line. So we call that dash thingy a vinculum. If you're wondering who Johannes Kepler is, he was a German mathematician, physicist, astronomer, and writer who made significant contributions to the understanding of the universe. He's best known for his 3 laws of planetary motion, which use simple mathematics to explain how planets move in elliptical orbits around the sun instead of circular orbits. This helped influence Isaac Newton's theory of universal gravitation. Before Kepler, they were kind of all over the place in the space world. They didn't quite understand how anything worked. There were some really, really, really crazy ideas about how things orbited that were made up because they believed that Earth was the center of the universe and everything orbited around Earth because Earth can't orbit. I don't feel us moving. That was generally the justification for it. So they had some really, really crazy diagrams out there where the orbits of planets looked like this, going around our planet, because when you look up at the sky, planets will go in what we call a retrograde motion, where they seem to go backwards, and it just didn't make sense. And then somebody, I don't remember their name, claimed that, hey, maybe the sun is the center, and we all orbit the sun. And that became pretty popular. It was about like 50-50 split, and it didn't quite perfectly explain the motions of the planets. Those really crazy ones that were made, where Earth was the center, was actually more accurate for quite a bit of time. Then Johannes Kepler came up with the crazy idea of maybe the orbits aren't perfect circles. Maybe they're slightly elliptical. Then they did all the math, and lo and behold, it was far more accurate, except for some of the planets really far out, because they didn't know about some of the planets that were there. And boom, he pretty much made it commonly accepted for how we pretty much view the solar system now, where the sun is in the middle, everything orbits the sun. Johannes Kepler is kind of the guy that got us all on the same page. So, a little bit of a tangent, but that is what he did. In class, we also did a little activity where we started to draw a little comic strip that helped us understand one of the vocab words we went over today. Yeah. All right. Have a good one.